Good morning. Thursday, we looked at the definition of determinant. And we looked at method for doing 2 by 2 and 3 by 3. We now have to look at determinants of higher size matrices. One such method is the method of cofactor expansion. So what is a cofactor? We have a matrix A defined as Aij. Define capital M sub ij as the n-1 by n-1 matrix obtained from A by deleting the row and column containing A sub ij. Right, so delete row I and column j. The determinant of that matrix is called the minor of that ij entry. And the term capital A sub ij, which is -1 to the I plus j times the determinant, capital M sub ij, is called the cofactor of the ij entry. Then cofactor expansion. N by n matrix where n has to be greater than or equal to 2. You can't do cofactor expansion with a 1 by 1 matrix. Determinant of A can be expressed as a cofactor expansion using any row or column of A. Right, so we typically say we're going to expand along a row or column. So you could have the determinant of A being this here, A sub I1 times the I1 cofactor plus the I2 entry times the I2 cofactor, so on and so forth. So this is expansion along the ith row. Or the determinant of A could be the 1j entry times the 1j cofactor plus the 2j entry times the 2j cofactor, so on and so forth. That would be an expansion along the jth column. Well, then remember that the cofactor is either plus or minus, then the determinant of that minor. And the minor is an n-1 by n-1 matrix. So you have 5 by 5. You're essentially breaking it down into a sum of 4 by 4 matrices. And this is the method that is used when you do the cross products in physics or Calc 3. cofactor expansion to find this 4x4 determinant. Notice in the previous slide, it didn't specify a row or column, which means you can use any row or any column. So generally, we want to look for a really convenient row or column to expand across. Row 3 looks nice. It's got 2 zeros in it. So instead of having 4 3x3s, we're only going to have 2 3x3s if we choose that row. So let's just write out what we're going to do. So determinant. 3-1 entry is 3. Times the 3-1 cofactor. -1 to the 3 plus 1 times the determinant of the minor. So that's the entry. You cross off that row and that column. What you're left with is your new matrix. So it'll be times the determinant of that 3x3 that's left.
How did you get the -1?
This is definition of cofactor.
Oh, right. Okay.
Plus 0 times, well, 0 times any real number is 0, so we can ignore that. Plus 8 times -1. That is the 3-3 entry, right? -1 to the 3 plus 3. Times that determinant.
And then what does this solve? Like
It's
what's the
determinant.
main goal?
Determinant. It's just a quicker way of finding determinant than using the definition. Right? Because how many terms would you have if you use the definition for 4x4? You have 24 terms you have to find. This allows us to reduce the problem to a sum of lower order determinants. In this case, 2 3x3s. Then you have plus, and then 0 times any real number is 0, so we don't have to worry about that. So this is our new determinant. We have two matrices that we found the determinant of.
So you could do it by row or you could do it by column.
Yep, row or column. And it's done the same way. You could use cofactor expansion for a 3 by 3. Right, but if you look at each of those, they're going to give you 3 2 by 2s. But we have a nice easy method for finding determinant 3 by 3, so I think we're just going to stop there and find that determinant. -1 to the 3 plus 1. Positive 1, right? Now just 3 times that determinant. -4 times -3 times 9. 12 times 9. -108. Plus 2 times 5 times -1. -10. Plus -2 times 7 times 6. 7 times 6, 42. And then double that, 84, and it'll be negative. And then minus, go the other way. -2 times -3 is 6 times -1, -6, minus 2 times 7 times 9, 7 times 9, 63, times 2, 126, and it's negative. Then -4 times 5 times 6. -4 times 5 is -20 times 6. There's the first term of the determinant. So that'd be the first term of the determinant. And we had -1 to the 3 plus 3. That's positive 1. Right, plus 8 times that 3 by 3 determinant over there. And then we just find that determinant the same way. 1 times 7 times 9. 63 plus -4 times 5 times -5. negative 100. Oh no, yeah, you're right, it's two negatives. 100. Negative 2 times 4 times negative 1. Plus 8. Minus negative 2 times 7 times negative 5. 70. Minus negative 4 times 9. 4 times 9, 36. 36 times 4, 144. I think it's negative, right? Yeah. Oh, okay, this one's tough. 1 times 5 times negative 1. That'd be the second term of that determinant. Six and 126. 132, 132 and 120. 252. How do I get negative out of that? 2, 7, and 9. That should be a positive 126. So it'd be 108 and 6, 114 and 120, 234. $10.84 is 94, 126.
I got 266.
You have to change the sign. That's one.
108, 6, and 120, right? That's right, 136, or no. What, 210? 10. Yeah, minus 220. 14. 14. Yeah, just 14. Which is what I got in my notes. So let's see.
It's two negatives, so wouldn't it make it a positive?
Where's the second negative?
Minus negative 120.
Yeah, plus 120.
108 plus 120 plus 6.
Yeah, that's the 234.
Oh.
I did all the positives first. And then did all the negatives. And you should get 234 minus 220.
I got it.
Okay, and then what do we get here? Is it only minus 70? Oh, that's convenient. So that's 163, 171, 176. So it's 176 and 144.
I got 250.
176 and 144. Should be 250. 163, 171, 176. 276.
Should be 150 though.
Add 40 to 276. 316, 320. And then 250. Three times 4, 42. 8 times 250. 2,000. 2042 here to 20. Three by three, we're going to use cofactor expansion. Because, look at that third column. It's 2 zeros in it. Coding is overloaded. Zero times anything is zero, that's nice, so we're going to look at that 6. What entry is that 6? Negative 1 to the 2 plus 3, now times the determinant. Negative 3, 4, 5, negative 8. And then 0 times anything is 0. Right, negative 1, 2 plus 3 is negative. Negative 6 times negative 3 times negative 8 minus 4 times 5. Should get negative 24.
What is the determinant like? Like, what's that? What's the purpose? Like, what? what's that negative 24 on the side?
It's just a mapping. So we will use it, you can use it to determine whether it's invertible. So if it's non-singular, it has a non-zero matrix, or a non-zero determinant.
Yeah, I mean, I know that, but like,
That's really all that I'm aware of. So it is useful for that, and then solving linear systems can be expanded from that. So when we look at linear independence, you can also use a determinant to do that. Otherwise, as far as I'm aware, it's just a linear, what's called a linear mapping, which we haven't studied yet. Yeah, it doesn't really play a huge role until you start looking at vector spaces. And we will be using determinants to find eigenvalues and eigenvectors, which is important. But we'll get there towards the end of the semester. So really, if you're looking for real world applications, it's really just going to be used for solving a system of linear differential equations. They won't do factor expansion. Of course they do. This is a case where I probably wouldn't use cofactor expansion normally. We don't have any zeros. That's a bummer. So, be the most convenient row or column, probably the first row. So let's expand across the first row. One entry times -1 to the 1 plus 1 times the determinant 5, 6, 8, 9 plus 3 times -1. That is the 1, 2 entry. So -1 to the 1 plus 2 times the determinant -5, 6, 7, 9 plus 4 times -1. This is the 1, 3 entry. Determinant -5, 5, 7, 8. first minor is not going to have a sign change. Negative 1 to the 1 plus 1 is positive 1. 5 times 9 minus 6 times 8.
Wait, what? Can it be 45?
Yeah.
I'm thinking 5 times 4, 9 times 6. Negative 1 to the 1 plus 2 is negative. Minus 3 times, what is that, negative 45 minus 42. And then negative 1 to the 1 plus 3, positive 1 plus 4, negative 40 minus 35. Seven. Three times 87. $261. And then 4 times 75. 225. 300, yeah. Three or 6 minus 261. That's going to be negative.
Negative 45?
Maybe a determinant. Which would probably, like I said, have been better if we would have done just the regular. Replace that first row with I, J, K, and there's your cross products.
I just got Vietnam flashback to your calculate.
That was the easy part of calc 3.
At what point does, like, in Calc 3, matrix doesn't really, like, there's certain things that you use the matrix for, but it's not really, like, a big part of...
Yeah, it's just cross product. Just
Yeah.
finding cross product of vectors. That's it.
Does it used more in, like, other maths?
Let's see. Are you including statistics in that? So yes, matrices are used a lot when you look at multivariate statistics. When you do multivariate random variables, it's matrices. Other than that, you won't really use matrices in pure math until really advanced, specifically tensor calculus. Because tensors are written as matrices. But that's really, really advanced. Tensors, I think, were invented with general relativity.
It always goes back to physics.
I'm trying to think, when did I use it in linear or in physics? Quantum. I think we used linear algebra in quantum. It's quantum mechanics. but I don't think it was matrices.
After your opinion.
A more advanced form of vectors. Are you familiar with the Ket and Braun notation?
Probably if you like, if I saw it, I'd probably just know what it is. Yeah, that, yeah. I've seen that.
That's linear algebra.
Really?
Because there's two ways to study quantum. Using calculus, where everything is integrals, which is a pain in the ass, and then linear algebra, which is the Ket and Braun notation. And then of course you have the DAG. You raise something to a dagger. That's apparently all linear algebra.
Wait, isn't the dagger just the derivative?
I don't believe so. Not in quantum.
Ah.
Derivative typically is prime notation, not dagger.
Well, I was probably confusing.
And then you have dot notation with respect to time for derivatives. But the DAG essentially switches a Ket to a Braun and Braun to a Ket in quantum. And as confusing as it's actually a lot easier than the calculus variation in quantum. I don't really remember using matrices outside of that, to be honest. Didn't really use linear algebra a lot in physics. Oh joy. What size is this? 5 by 5. But
Zeros.
we have basically all zeros, which is nice. So you get one guess on which column I'm using. I'm not going to write the -1 this time. What entry is that? So their sum is even, going to be positive. We do, of course, have the issue of being left with a 4 by 4 determinant.
So would you have to do it again?
And hope that we get a nice row or column. Which it does look like we did. We have 4 convenient choices. Next, obviously, we're going to do cofactor expansion again for that 4 by 4. We can do column 1, column 2, row 3, or row 4. Row 4 is definitely the best option. I'm going to do is actually just start a new slide for this. Now remember, it's going to be 5 times whatever this cofactor expansion is. So let's just write 5 on the very outside. First 2 terms are going to be 0. That's nice. What entry then is this one? New one.
It's gonna be odd.
It's not 3, 4.
It's 4.
It's 4, 3. Odd, so it's going to be minus. Again, I'm going to be a little bit cheeky. That up. And then look at what we're left with. Cross out row 4, column 3. That's the 4-4 entry, right? Even, so there's no sign change. There we go. Oh, I have to go back to you. For each of those 3x3s, we could do cofactor expansion again.
I mean, it wouldn't be that bad because you have
Because those 2 rows of zeros, it's not terrible. Again, because those, or not 2 rows of zeros, but because those 2 0 entries, either method's going to be pretty fine. I'm not doing cofactor expansion. Okay, why don't you do that? Remember, it's going to be negative times this whole thing. 2 is 4 times 6, 24. 0, 0, 0, minus 6, and then 0. Minus, going to have a very similar outcome. 12, 0, 0, 0, minus 3, and 0 again. (24 minus 6, 18, right? Minus 12 minus 3 is 9. Negative 18 minus 9. Negative 27. Times 5.
Negative 135.
Negative 135, there's your determinant. By the way, none of these determinants were 0, so all those matrices were non-singular. Property of determinants, I don't know if this has been proven in the videos already. Determinant of a product is the product of the determinants. We're not proving it here, we're just verifying it for these matrices. Do you recognize those two matrices?
They're what we used before.
No need to reinvent the wheel. We already found those determinants. So determinant of A, I believe that was number 3, right? Determinant of B, number 2. Negative 45 times negative 24. Oh, it's positive, right? What's 45 times 20? All right, what's 45 times 2?
900.
Times 10. There's 45 times 20. 45 times 4. Now 900 plus 1, 80. 80. There's 45 times 24. See, it wasn't that difficult to do without a calculator. Just have to remember your algebra. That one's the fun part. Finding A times B and taking its determinant. Oy vey.
What did you say?
Oy vey.
Oh.
You get to verify that this is the matrix you get. Actually, this might be a good opportunity to show off matrix multiplication in the calculator.
Will we be using the calculator on the exam?
Unless the question tells us specifically not allowed. All right, so remember matrix entry in a calculator, 2 ways you can do it. Menu 711, then you have to enter the size of the matrix, then you just enter each entry. Or you put it in brackets and separate your rows with semicolons and each entry in the row with a comma. Times. With the calculator, you can just do regular times. You can't do that in Wolfram. I think product of matrices is they use the dot command to do matrix product? So there's your matrix product. Go back. Verified. Now we have to find that determinant. Oh boy. I think this is going to go on another slide. Two ways you can go about this. You could use cofactor expansion if you wanted to, or you could just use the definition. There's really not one way that's more advantageous than the other. 8 times 33 times 48. And of course it's negative because there's a negative number in there. $12,672. 3 times 30 times 8, and again, there's going to be a negative there, so this is minus. This one's actually not bad. What's 9 times 8? 72 times 10, 720. This will be plus 18 times 35 times 12. $7,560. This is going to be minus and negative. This is plus. 18 times 33 times 8. $47.52.
How's it positive?
Minus and negative. Right, now we're going the opposite direction, so it's minus. It's going to be minus, looks like another negative. There's only one negative term. So plus 3 times 35 times 48. $50.40. Minus, and this will stay minus. 8 times 30 times 12. It's 8 times 12. what is it, 106?
96.
96? 96 times 3 is 288, and then times 10. Is that 1040? That's what I meant, 1080. So that property's been verified.
Is that a general thing, or is like?
Yeah, that is actually true. I think I prove it with with the next video when we look at row operations and determinants. I think that's where I prove it for the general case. Well, use this example where we just showed for these two matrices, determinant of A times B is determinant of A times determinant of B. Would those two determinants be equal? Why? Well, what does that do with matrix multiplication? Because you would agree A, B, and BA are not the same, necessarily. But I agree, they are equal. Why?
Is it because you can split it up and then therefore it becomes multiplication, I guess?
What do you mean multiplication? We have more than one multiplication now.
If determinant of A times B is equal to determinant of A times determinant of B, you can assume that determinant BA is equivalent to determinant B times determinant A. And you just flip.
And those two determinants are real numbers, which then becomes just multiplication of real numbers, which is commutative, and the order doesn't matter. So those two determinants would be the same. Question on cofactor expansion.
So the next step is like reducing it down for operations, right? To make it easier.
That is what we're going to look at after the exam, yes. Using raw operations. And it is the method that I will use. Because it's just easier.
I love how you introduce a concept that is hard to grasp and then just give it something that is significant and easier to solve.
Well, that's the whole point, right? Do something that's really tedious and then introduce you to the shortcut, and then you appreciate the shortcut that much more.
Maybe that's just math manipulation.
Well, that is math. Manipulation. Could also be math, who knows? how did the first project go? We still want some more time.
Getting it honest, I did have to, kind of, in a sense, bullshit my way through the rest of the questions because I couldn't figure out how to prove it, so I just did what made sense to me. The problem is I'm trying to make it sense to you.
So let's do this. Let's push it back a week. If you already submitted the project, I can just go ahead and clear out your attempt on Canvas.
What do you guys think?
Give you another attempt.
I don't know who the other two.
So that's what I'll do. I'll go ahead on Canvas after class and clear out your attempts. I think I can do that. If not, I'll just grant another attempt. Because that I can do.
That sounds easier.
Yeah, but then there's multiple files uploaded.
Oh, wait.
So I'd rather just clear the attempt so that there's nothing uploaded.
Yeah, but this is the new attempt over, right? The second. What?
It'll show me all the files.
Oh, I feel so bad for
I
my
believe.
other. I feel so bad for my other.
I believe that's how it works on Canvas. Blackboard, well, the old Blackboard, it actually broke it down, attempt 1, attempt 2, attempt 3. I don't think Canvas does that.
Well, Canvas does make the attempts. They just give you the one. It's just you can just look at the latest one or look at the highest rated one. It's
Yeah, remember, that's on your end,
oh yeah.
not the
That's right.
instructor end.
Yeah, because there is a homework that I could do like implement attempts, and it took me 20 attempts to get the perfect 100. And I feel so bad if my instructor saw all of that.
Out of question, I'll take
I just abused the attempts.
What's the exam cover?
Everything,
Everything.
like we've done so far, yeah,
Okay,
including today, yeah.
Okay, alright. Besides like homework and stuff like that, do you have anything else with this stuff you look at?
Books, the practice exercises, lecture videos.
What's this?
Oh, we get it.
So you can write anything you want on this sheet double-sided. The only restriction is it has to be handwritten. Otherwise, anything goes fair game. And then you can bring the sheet and use it on the exam.
What's
And then you bring it in.
wrong with everything around? This is the first time I've seen something like this. You guys-
So that it's to keep it consistent, so that someone doesn't, use an insanely huge sheet of paper. Because I've had someone try to do that before. So this way I know it's my sheet. The exam is on Thursday. Make sure you bring a pencil or black ink pen. That's all I will accept for writing on the exam. Calculator, make sure your calculator is charged. And don't forget it if you're not using mine. So you don't want to come in, try to turn on your calculator and find out that it's dead. That would not be good. Right? So make sure it is charged.
Can you give me your email? So I'll send you.
Otherwise, I don't think you need
Oh
anything
wait,
else.
it's right there.
I'll do
It doesn't make
6 and
sense.
7.
Okay, never mind.
I spent last night doing the first grade.
See you on Thursday for
And
the
then
exam.
I use text for TS.
You know what? Let's
But it's like infinitely harder because it's like an actual program. So
Yeah, I don't know if you wanted to to do it, but I can. So I'm like 12 minutes away. So like
whenever,
last night,
I
I'm
mean,
like,
yeah, I don't.